So probably most of you saw Niko's talk yesterday. This is Niko Kriegeskorte over here for those of you who don't know him, in the middle. And we thought we would take this opportunity hosting a distinguished visitor, someone who's not part of our center, but who shares many of the interests and concerns and kind of broad research agenda that the CBMM researchers do, the ones who you see up here, in trying to understand, well, how the brain works, how the mind works in the brain, especially oriented around visual perception, but with an interest looking beyond vision, and really trying to do this drawing on tools, modern tools from engineering, especially deep networks, but not only deep networks. And so we thought we'd just have a discussion about questions that were, some of which are questions raised by the work Niko's been doing, and some of which he raised yesterday in his talk. But for those of you who've come to other panels like this, it's sort of familiar, in some ways a familiar set of questions, but we thought mixing up the discussion a little bit with some new participants would be a good opportunity to expand what we're thinking about. So I just came up with a set of questions that were partly based on an earlier discussion with Niko. He has some other questions that I think he wants to add. There's not any sort of formal plan here. I'll just say a couple of questions that I think we're all interested in, and then mostly turn it over to the other panelists to weigh in on that. Josh had some, I think, helpful preliminary remarks, which we might start with after I introduce his questions. So things we're all interested in. What does it mean to understand, or quote, understand the brain, and especially the ventral stream, in the era of deep networks? Can we come up with better, richer ways of comparing representations in models and brains, which are more revealing of how brains actually compute? So Niko talked yesterday, and he's been one of the leaders in addressing this question. But I think, one of the things I like about him is that he's appropriately dissatisfied with all the things that he can't still do yet, right? So what, in a sense, what are the new frontiers of comparing representations in behavior, in brains, in models that, for example, can get beyond similarity, as great as similarity is? How should we understand the top-down and recurrent processing that occurs in vision and its interaction with feed-forward bottom-up processing? Again, an issue that you raised yesterday. Ways to compare integrated models of bottom-up, top-down, and recurrent processing in a network to neural data in both humans using the tools available for human neuroscience, but also in non-human primates. A question now that I'm very interested in, but I know some of our other panelists are too, to what extent can we understand vision as inverting a generative model? And if so, where is the generative model in the brain, and how is it used in online perception, learning, or imagination? Is it in the top-down connections? Is it somewhere else? Is it actually used online, or is it just used for training? Is it used more for imagination? And how does it interact with the feed-forward parts of things? And then how can we scale the successes that we've had in understanding object recognition of the brain to other aspects of vision, other perceptual modalities, and also beyond perception? I think just big open questions for how this paradigm might carry forward for us. Okay, so those are our questions for discussion. And Josh had, I think, the very helpful suggestion that we might start off with just sort of putting on the table, mostly so that we can set aside some of the basic objections that one might say if one wanted to object to the program of, say, using deep network centers in the brain, right? So
yeah, sure. I mean, I think these are probably widely appreciated by most of the people who are here. But we mostly just didn't want to reiterate the usual arguments. So one of the standard examples that we often talk about of why this might be not a very good model of human learning is the fact that networks need to get trained with vast numbers of label training examples, right? Probably more arguably than humans ever encounter for most problems. People will often comment on the fact that the learning algorithm is probably not very realistic for the brain. Another common objection is that the classification task that these kinds of models are typically trained on and used for is a pretty impoverished view of perception. We can do a lot more than just classify things. Another class of objection is arguably that the models end up being kind of hard to understand in a lot of conventional terms. A lot of people find them sort of complicated and messy. There's no principles. And there's sort of a class of aesthetic objections like along those lines. Something that maybe some people also know about are the existence of adversarial examples. These are stimuli that you can engineer, given the fact that you have complete knowledge of the network, to kind of fool the network in ways that are very counterintuitive for a human. And so some people think that is very damning for the whole program of taking this seriously as a model of perception. Others wouldn't. But what am I forgetting? What are some of the other things? You probably have some.
We can save them for later.
Well, are you thinking, Josh, those are points that have been raised by many people many times. And I'm just trying to understand your point in putting them out there. You want
So I could also, we could also regurgitate like the standard lines of defense against those objections, right? Which is like, so Jim would say with respect to the issues with learning and the number of examples that we're not necessarily trying to model learning. What we're interested in is like the state of the system after it's developed, and even if it was trained in a way that is maybe not like how the brain gets trained, like the final state could nonetheless be like a useful model.
And also, when we train on these millions of examples, we're conflating probably what part of that burden was offloaded onto evolution. So we're trying to make the system do evolution and do ontogeny and phylogeny at the same time.
Yeah, for sure. What else? With respect to adversarial examples, I guess the counter argument is that, well, we don't know that they don't exist for the brain. We can't derive them because we don't have perfect knowledge of the brain, right? And maybe if we did, we could. What else should we say?
Well,
You probably have some lines of defense.
the uninterpretability question. I think Niko presented some ways to kind of visualize what some of those units were doing, and I know Ode has worked on some of this, and other people are thinking about that. So, actually, I'd love to hear more about that at some point.
I think that would be good to talk about, actually.
And I just going back to adversarial examples for a second, what does it mean to construct an adversarial example for human vision? There's metamers and things of that sort, right? But the definition of an adversarial example in computer vision is based on our own subjective perception that these images are more or less the same, right? So what would the equivalent be that a computer thinks that they're the same and people think they're different?
So maybe, I can try to answer that. So usually these adversarial examples are constructed by with full knowledge of a particular network, right? Mm-hmm. So if you could do that if you do it for a particular network, then adversarial example will be something that looks like a bird, but the network classifies it as a bus with high confidence, right? And that's going to work for exactly that network, and not necessarily equally well for other networks, especially if they're not trained on the exact same images, right? Now, there's a whole literature looking at the extent to which these adversarial examples do generalize, right? And I'm not saying sort of this is all trivial. Of course, the basic point is that for any learning system, biological or artificial, you can always place an example in the region where the boundary it's learned is not perfect, right, and fool it in that way, right? So we have to get over sort of this very naive overinterpretation of adversarial examples, right? But they do generalize to some extent, right? But there's still the question, to what extent do they generalize, right? So if you had an adversarial example for a particular person, it could be an image that looks like a cat to me, but everyone else thinks it's a dog, right? So it's a little bit like the dress.
Maybe even more profoundly, right? Something that looks systematically different from what it actually is, like as in all.
How do we know what something actually is?
Well, wait.
There's
go all weird and philosophical. Like the whole, all of perceptual psychology is based in large part on illusions, right? Cases where we know what the object is, and there's a systematic, widespread, shared misperception of the thing. Maybe those are the human adversarial examples.
we
should stay with the bird and the bus, right? So I think it's a bird, but then by walking toward it and interacting with it more, I could convince myself that unbelievably, it is the other.
Every so often we see, this is well known, in clouds or rocks, it looks like a face for a moment, and then oh no, it's not, right?
but no one says that's a face.
Right, but
like a cloud that looks like
it's briefly, briefly something that's one thing that looks like something very, very different, right? Would you say those might be examples of things that are kind of like adversarial images? That are, to me, those are the things that are most familiar. Right? I can count on one hand times in my life when, wow, I really thought that was something, and then it turned out to be totally different. But that does happen every so often, right?
So
I think the adversarial examples are probably best thought of in the slightly more general framework of the context of metamers
Yeah.
and the context of similarity and two representations having different similarity structure, right? And this is sort of an extreme case of that, where we have one representation, for example, conventional labels, that gives a very different answer from another one.
Right. I didn't want to get us going down a rabbit hole that's maybe somewhat tangential to the questions of intelligence in the brain. I think actually we could turn this in a slightly different direction and ask, what can we learn from adversarial examples about representation and intelligence?
Or if that is something that we can learn.
Yeah, so we know we've learned a lot about human visual cognition from illusions, right? Because we know that there are these things that seem where there's no contrast, and yet we see a contour, for example, where we see a surface. And that tells us something about the nature of our object representations. And in some ways, actually, I feel like a lot of those lessons haven't even been really internalized into the work on computer vision. We don't know, we don't have a lot of examples of deep neural networks that show the complete array of visual illusions that humans do. And I think maybe that's something to think about. Maybe we should be trying to build networks that exhibit these visual illusions.
Or study what those illusions tell us.
Yeah.
Are not kids just adversarial system? They are learning, they are making mistake after mistake. Well, no, sorry. This is not mistake. This is the way the system takes in, actually. Yeah. So don't take that dog for that.
I mean, we can test whether we are really affected by adversarial examples. I would like to ask the panelists to be completely honest for a moment. You all look human to me. Who of you is secretly an ostrich and is consistently fooling us? Is there anybody? Speak up, please. I suspect that in the visual domain, we are very robust against the kind of adversity that our networks are seeing. Tickling is something like an adversarial example in the touch domain. But I don't think that we have an equivalent to this in the visual domain, maybe because we are evolved to be robust against this.
Well, we are all natural, right? So the adversarial examples are evil concoctions constructed with full knowledge of one person's brain, right? So they're totally, that's why also as machine learning, it's not a problem. The recognition system works fine in the real world for all practical
the
purposes.
probability of encountering that would be zero, right? Yeah.
No, not one person's brain. One linear function approximator's network. That's not the same thing. We don't know whether that's the same thing. And most of us think not.
Right. And
It
so
might be.
let me expand on that, because I think this is a way to bring it into contact with one of the questions I asked, my favorite question, or one of them, about generative models, right? It seems to me, I don't know how to state this rigorously or prove it, but it seems to me that if you have a generative model, and that part of perception is not just a feed-forward process, mapping from images to some feature space, but actually coming up with a scene interpretation, which in some sense has to re-render back to something that looks very much like the image you see, that would make you robust, not to all adversarial images, but to certain kinds of adversarial images. It seems to me that system would either not nearly as sensitive to, or maybe just not sensitive at all, to the kinds of adversarial images you have, where either you make a very, very, very small tweak to the image, like one that's normally in the noise level, and then it transforms the interpretation from the category that it would be seen as to one that's very, very, very different, right? In a Bayes classifier, you can push things to a category boundary, but you can't necessarily just push things. You can't necessarily get the network to make arbitrary mistakes, especially if you constrain it with a likelihood function that it has to look like the image. Also, there are some kinds of adversarial images. They're not ones that are as widely used, but the ones that Jeff Clune and colleagues came up with, people know these ones, where you don't tweak an image of a cat to look like a bus, but rather you take some sort of texture that doesn't look anything like a natural image that's generated from some genetic algorithm that they use to search over a space of sort of weird object textures, like things that that might look like the ceiling out there. They don't look anything like a natural image, but yet you can still tune them until they get classified as a banana or a cat or a bus or whatever you like. Again, things where the interpretation would just never render back to anything that looks like that image. So I don't know if other people share that intuition or anybody wants to disagree with it, but to me that's one place where considerations about adversarial images might tell us something about the architecture of the system.
And someone should do that, right?
Do what?
Someone should take one of these generative models and try to construct adversarial images.
Well, the problem, and again, this is something Josh has said, I think you guys said this last night, right? If the model is wrong, right, if the model is, like, all of the generative models we actually work with, it's easy to come up with cases that they just don't cover, right? And then for those ones, you know, you could potentially do that. It's, in some sense, this is a hard thing to actually falsify with any simple generative model, right?
Josh?
Yeah.
I think it's not even clear how you would get the adversarial model into your brain, because you don't see what's on your retina. You cannot see what's on your retina. There's not an image there with a high resolution. What you see is the rendering produced in your brain. You don't produce this rendering during some training phase. What you see right now when you look at me is a 3D rendering generated by your neocortex. And it's based on very sparse data coming into your retina, and it's made to conform to that data, basically to conform to the, to produce expectations, to allow you to interpret this few samples that come in. But it's a configuration.
Who's you in this model? You said what you see
Me,
on your
me.
cortex. No, he said what you see. Who's you?
It's
The
Some
owner
other
of
part
that
of
piece
your
of
cortex.
cortex, yeah.
The magic man in the back?
So there's a system that makes a protocol of what you attend to. And this is the thing that scans what you build. There are two systems. One is building the representation, keeping a stable model, and another one is the thing that reports right now on you having that experience of a part of it.
Okay.
We can switch question.
I think maybe
Do you wanna-
before we switch question, I would put a slightly different perspective
Good.
on it and see the adversarial examples less as a fundamental challenge to a particular system, but as a method of generating stimuli that help us to adjudicate between models that we're interested in, right? And that goes in the direction of, you know, Metamers and adversarial examples, also the cases of constructed synthetic stimuli where that make very extreme predictions for a particular model, right? And so the more general framing of this, from my perspective, is experimental design, right? So we have, let's say, 100 neural network models, and our goal is, and they all perform the task, and maybe they all, you know, by our measures, do quite well at explaining the representational spaces. And now we want to construct stimuli that help us adjudicate between them with very limited and expensive data, right? So we want to decorrelate their predictions, essentially, right? And I think that is potentially a very interesting way of thinking about it, and one that sort of synthesizes this old debate between natural stimuli and artificial stimuli, right? Because they're going to look somewhat natural, but they're going to be artificial.
Some of the classic, I mean, or at least the classic metamers that come to mind for me right now, I'm sure I'm not thinking of all the right ones, are ones where the locus, kind of maybe even consistent with what Yasha was saying, is sort of at the, like a primary sensory cortex, right? Like whether it's color metamers or texture metamers, they're things which, or like your sound things, they're things which like match the statistics of, you know, V1 or potentially. And then that I mean, it's an interesting idea that maybe if there's a generative model, you know, it doesn't go down to the retina, it maybe goes down to V1. And so what matters is, does it, you know, if it looks like an image at the level of V1, then it's good enough, right? And so that might be a way, that might be consistent with metamers again, but that's not the same thing as like a category metamer. Like it looks like a dog, but it actually to level of V1, or rather, it looks like a dog to the high level of the network, but it looks like a bus to V1 or something, right? Which is effectively what we're talking about with some of these things. And that's I don't know how that comes into your picture, but if we want to move to a different topic, do you want to say what you were going to say and then, or do you want to follow up on this?
Before going to a different topic, if I may make a note.
Sure.
4 decades ago or so, Bela Julej from Dallas was interacting with Salvatore Dali, who had an apartment in New York. And Salvatore Dali used to use, to do stimulated illusions. And Bela was interested in what is it, that is involved in creating those illusions. And I wonder if the fMRI-based approach can actually, explain that. And the neural
Explain
networks
what?
are
Dolly illusions
Explain
or
what?
the Bella
the,
Eilish type?
the dynamics, the complexity involved in creating those illusions. By just looking at fMRI images, is that or neural nets static are going to help us resolve those questions?
Well, you can't answer any of these questions by just looking at fMRI images. You need fMRI images and a theory of why they work, and the fMRI images can provide some evidence.
We can
and
leave it
support.
open. Maybe if we have time at the end, we can come back to the questions of art, because that is interesting. But, do you have a direction?
What was your first question? You gave such a
Yeah.
long list that I
I'll
liked
wait
the
that.
first one. I remember that.
What does it mean to understand the brain? And the
Oh,
era
wait,
of
no, but it
computing?
had the ventral stream in
Yes.
it.
So no, I said, what does it
What
mean
does
to
it understand the
ventral
ventral
Yeah. Sorry, I lost my mind. What does it mean to understand the brain, and especially the ventral stream, in the era of deep networks?
Yeah.
And can we come up with better, richer ways of comparing representations in all? So I'd like to know basically what's beyond RSA. I think RSA or RDA or RDM is really cool. I've worked on similarity things myself. I have a lot of respect for those methods. But I feel that we're going to need to go beyond just simple low-dimensional vector space or even high-dimensional vector space ways of understanding. So do you want to comment on that?
I guess I was interested because we have both Niko and Nancy
Yeah.
on the panel.
Mm.
And I see you guys as representing sort of two extremes in what it means to understand the ventral stream, where I'm going to grossly mischaracterize these and you're going to have to correct me, but you're more like, once we've got the set of representational distances, we're done. That's an extreme. I'm caricaturing you. And Nancy's like, once we've got all the modules and their internal computations, we're done.
I don't think that at all.
Okay,
You
so
like putting everything on one.
good. So there's something different about the way, even how what you're looking at response preferences, and you're looking at geometries, and so.
But these are not opposed. I don't know how to
Okay,
think about
so
it, but
good.
I
So
don't see
that's
them as
like, are
opposed
they
at all.
opposed? Are they parallel? Okay, good.
No. I mean, finding, I just like big effects. And so when I look at the ventral pathway, it's like, let's pick off and identify them first, right? And let's go from there. But just because there are big salient category selectivities in the ventral pathway that are like the first thing anybody sees when they, do neuroimaging, doesn't mean that that's not an explanation of anything. It's just like a big effect that should figure into your ultimate account of how vision works or how the brain is organized. And I actually think that the kind of stuff Niko does is a cool way to try to characterize. We want to know all kinds of things about those regions. We want to know what's represented in each. We want to know how they compute what they represent. We want to do all that stuff. And I see these classes of models as, a cool approach to that. So.
Yeah. One thing that I think comes out in that is you can either think of the ventral stream as one big chunk of cortex and think of all of it at the same time, or you can look at little pieces of it. And sometimes we're doing representational similarity over the whole chunk, and sometimes we're doing it over little pieces. Those seem at odds. Like, is the answer
Well,
a
except
big
that
one? Or is the answer a little one?
you're a co-author with Michael on that paper.
I
right?
know.
So these guys, I
I'm
don't know.
hinting there.
Yeah.
Tell us that.
So I'm
waiting
okay.
for it.
Okay, I find those data fascinating and
Wait,
paradox.
tell us what they
Okay,
are.
so basically, what those guys find is that if you do an RSA on just the FFA or just the PPA, right, which we know are functionally extremely different. We know this from other methods like, intervention methods or brain damage or something. We know those regions do very, very different things. And yet, weirdly, the RSAs are really similar. That's what you guys found, right?
On what set of
For the FFA and the PPA.
On what set of images?
What images?
Yeah,
Well, what did you
At
guys
the
have?
category level, right?
at the category level.
yeah.
So
Mr.
this is sort of
Yeah,
what,
right.
what I wanted to say when you said you like effects. I say I also like big effects, but I also like detailed signatures of behavior and brain responses, right? So I like not averaging voxels together and not averaging responses to two different images together, because each image is a unique percept and separate. And if not, then I want to know about it, right? If the brain represents two different images identically, then that's a very important piece of evidence for the nature of the representation, right? So I hope that, but at the same time, I agree with you that we need strong effects and we need to summarize the data somehow, and we need to look at statistics that are comparable between different individuals, and every individual brain is unique, and we don't have unique neurons that are conserved across individuals, right? So there are some big questions. Getting back to the first question on the list. What does it mean to understand how the brain works, right? What is our target? What are we? When will we ever be satisfied? I think it's a question that we don't ask enough, and we should discuss. When is this over, right? So one thing that's happening is that AI is sort of taking over in a way. So let me just sort of provocatively suggest that 50 years down the line, people are going to look back at the history of brain science and say, well, biologists tried and they didn't really, manage to do it. And then artificial intelligence took over and, understood
What's the it?
What's
the it?
Yeah.
Object recognition? What's the it?
how the brain works.
But what does that mean exactly?
So
take object recognition. I
Let's
think it's
say
a more practical.
AI just conquers more and more tasks, right? It conquers vision, it conquers motor control, robots of many shapes and sizes.
In terms of explaining how it works in the brain?
Are we talking
Or
about just doing
solving
things?
the task?
Being able
Well, okay, just solving. This is a bit meant to be provocative, right? So
good.
it's sort of engineering, but of course it also means we can build a robot that has a body that's more like a human, and then it's gonna have motor control that's more like a human, right? And at some point, without caring much about the biology, it could be that history in retrospect says that AI engineers solved the problem of how the brain works. I wonder about that, right? Maybe not, maybe yes. I hope not. I think we should be thinking about criteria and tests that are based on detailed signatures of human behavior and animal behavior, and human brain activity and animal brain activity. But it's up to us to define that as a standard to judge by whether to the degree to which we understand it, right? And if we don't do that, then at some point everything that we care about is just going to be thought of as some details don't really matter, because fundamentally we can build this kind of thing.
Well, I mean, let's put out. All right, I could put out one example, or an example of things that currently, at least the kind of deep networks that say you guys have been using, don't, or it's not clear that they explain. They could. It's not. I'm not saying a neural network couldn't do this, but these are things which we would like to understand how they work in the brain. So if we're talking about vision, we could say, well, think about all the functions that vision supports, right? All the we form our beliefs about the world in at least the immediate scene in front of us through perception. Maybe people tell us things, but we have all these fine-grained beliefs about what is where, and then that's the classic notion. But also things like intuitive physics, what can happen, what can I do, affordances for action, things that I have to be aware of, and or other people's thoughts, all the mental states, right? So these are all things that we get from vision, and that we at CBMM are really interested in how vision supports. At the moment, we don't have deep networks that do those things, but we know the brain does things.
Yep.
So we could ask, well, how do we understand those things? How do we either push deep networks to become tools to give us ways to understand those things in the brain, or what other kinds of models do we need, and what kinds of ways of comparing representations? Because basically, until we can understand how the perceptual system or the other parts of the brain that it represent those aspects of the world that we clearly as humans can act on, then we haven't really understood the representations in the brain of the world.
I agree.
Can I ask a follow-up question about this? It's more of a thought experiment. So suppose that I told you that I have some function. That function could be anything. Let's say it's infinitely expressive. And I'm going to give it any inputs that I want. I'm going to give it, let's say, all the inputs, all the sensory inputs that humans experience, and I'm going to train it so that the outputs that it produces are the same outputs that humans produce. And I have unbounded amounts of training data. And then eventually I show you that this function, once I've trained it enough, will take the same inputs and spit out the same outputs. Now, it has to logically be the case that with infinite amount of data, with an infinitely expressive function, that I will eventually succeed in that task, right? So it's actually, in my mind, completely uninteresting to say that AI will one day explain the brain, because that's like saying because it's so underspecified, right? It's saying like if I have unbounded computational expressivity, unbounded computational power, unbounded sample size, I can solve this task, right? I think that's almost a tautology, and I don't think it adheres to what we would say, what we mean when a scientist says we've explained something, right? Explain something means provide insight into the underlying mechanisms, the things that are going on inside of that function.
I got to push back on that.
Okay, go for it.
Because I think that's a key kind of crux for me when I give talks about our work, and this comes up a lot of us, like what scientists mean by understanding, right? So I think that was sort of one of the questions,
Very, really
right?
important question.
And you said what scientists mean by understanding is, and then you said some insight. And I just wrap that as like a circular statement. What scientists mean by understanding is something that they want to not define, right? And so I think what scientists actually deliver as understanding is predictive power. And that's what allows any science to be not a pre-science, but an actual science that has applications, whether it's fixing
Jim,
the
that's
brain.
not going to work, right? People could predict the movements of the planets long before they understood the, theories
If
of
they
gravity.
did not try to do prediction on a defined goal, none of that
Yes, but
Newtonian
you said prediction is enough, and I'm
No,
showing you
I
an
did
example
not
of prediction.
say it was enough. What I'm saying is saying we need insight is
No,
not
okay,
enough.
Jim, I take
So-
this credit. I think you're exactly right. I agree with you. One shouldn't have these wishy-washy statements about insight. I think and in fact, I think Niko is more or less saying what I'm about to say, which is that you can't just judge success based on the degree to which this black box's outputs match people's outputs. You have to also measure it on the basis of how well the things that are happening inside of that black box match the same things that are happening inside of our brains. And that's exactly the whole point of why we are measuring neural activity in the first place. But you have to be careful, right? Because, and again, I'm kind of just echoing what you said already, we don't care about little biological detail in the brain. And so we have to come to some consensus about what things we care about and what not. Like I just came back from a meeting of economists, and it was a joint thing with economists and psychologists. And it was very interesting because for economists, they have one thing that they really care about explaining, which is choices. And neuroscientists don't have anything like that. We disagree about even the things that we want to explain.
Well, look, so Sam,
Max had a
Yeah.
question. Sorry. Did you want to?
Well, first of all, Sam, I think what you said about having what goes on inside the brain match what goes on inside the model, like suffers the same issue that you pointed out with infinite everything. And I guess a personal question, if we don't believe in it or care about insight or understanding or something like that, why are we doing this?
Yeah, I want to jump in on that actually. So I'll represent the complete opposite of you,
I didn't
Jim,
get to,
in
I didn't
terms
actually
of
get
what
to
we
com-
want.
I didn't complete my argument.
Oh,
I got cut off, but go ahead.
Sorry.
Yeah.
Okay, I want wishy-washy insights as an answer. I consider that part of the answer we're looking for. I want a predictive model, but I want the wishy-washy insights.
Can we turn wishy-washy into intuitive?
Yes, I have.
Okay.
I have a formulation.
Okay, good.
It has to pass the toddler test. What's the toddler test, you ask? The toddler test is the curious mind that goes, how does this work? Why? How? What? In succession. You have to give short answers, but they can get deeper in either mechanistic, how? How does that work? How does that work? Or sort of, I thought, why? Why is that the way it is? And so it's like I want a nested set of understanding that's short, compact sentences that can be unpacked into many levels of how and many levels of why, and I want a model. And I think that just having the deep net doesn't let me answer the toddler's questions. And that's so I
You don't
want
give your
both.
toddler the deep end?
I mean, I'd be like, well, didn't you see the 60 million parameters? That's the
So, you know, it-
I
yeah.
know it's so I think getting the wishy-washy answer is part of the whole answer we're looking for. Just standing on that end of the line.
So
I
which,
mean, it's-
which
it's-
questions in deep nets are not answered to you in that way? Like which
What are
ones?
the
which-
features that tell apart animals from us? Like, can you describe them for me?
Well-
Why do we see these kinds of separations? I don't know. There's so many questions that
It's not- I mean, it's
The
not
latter,
obvious.
The why do we see these kinds of separations, I think, is exactly the kind of thing that in principle a deep net might be
can
able to
get
do.
us there.
Yes,
That's right.
you can train it
actually
with different
very
things.
I want to be able to actually
see
answer
what
them,
kind
right?
of things
Yeah,
come
so
out.
that part, yes,
I know.
yeah,
It's actually like it lets us have computational existence proofs of the kinds of things that can be learned with certain kinds of constraints. That's what I think it is really good at answering. But it doesn't.
So you want a natural language explanation? Or is
Yeah,
that
that's a good
Because like,
question.
how do you ride a bike? I mean,
Well, I
you
think
can't
that's a
explain that to
classic, we
someone,
can't,
yeah.
and we don't understand it.
But if you ask someone to
either.
explain
Oh,
the physics, no, but if
I
you
like
ask someone to
that.
explain the physics of bike riding, like why is it stable, why can you do it, that would pass your test.
Yeah,
right?
you
I mean,
could walk through the.
I couldn't do it, but
Yeah, someone could. I don't know enough about. That's right. There's angular.
But I mean, it's possible you're just going to end up disappointed. I mean, seriously, right? I mean,
What, you mean that
there
with deep
isn't
nets or
that
with
level.
everything? And
There
just
isn't
with
that
with
level.
everything, right?
like take modern physics. So physicists might sometimes say that with the advent of quantum mechanics and then quantum field theory and things like, maybe it's no longer passes that test, or maybe it does. I mean, the right physicist, like if Alan was here or something, could do that. Like, so a really good physicist who's really good at explaining the difficult stuff of modern contemporary physics could actually do that. And you might say that
Like, that's
somebody
a good
could do that.
understanding.
Yeah,
actually,
like Jeff Hinton could probably do that for deep networks. I mean, one of his things that he's really good at is explaining intuitions about things like why does dropout work and why does that.
But just there's a really important distinction here between the kind of explanation that someone like Hinton would provide for why things work, and I think what Talia is asking, because here's another thought experiment. Like, the NASA sends a rocket to the moon, and let's say that they use Newtonian mechanics to determine that rocket's trajectory, and that trajectory might be some complicated thing, right? And now you ask, how did you send the rocket to the moon? The answer that you want from NASA is not, well, it took this trajectory, and then this trajectory, and then this trajectory, and then this trajectory, and then it got to the moon. The answer is Newtonian mechanics. That is in the same way that I think that the answer for why deep nets behave in particular ways are the combination of the architectural principles and the algorithmic principles, right? Those are the explanations, not these parameters or these particular decision boundaries. So.
This
feel
kind
like
of architecture, this number of units, you need this kind of principle to extract these kind of features. So maybe understandings of like which nets do better and why, not just this net does it good and how.
Yeah, I feel like we don't disagree that much. I feel like we all want a multi-level understanding. We want to some extent an intuitive understanding, and to some extent sort of theory, rigorous theory.
Jim has expressed almost the same belief that Talia just said, I think, right? Like, that maybe what we want are principles of architecture.
I agree with what Sam said about you want to predict the internals, right? So you you need to be able to predict things, but people are pushing on the word prediction. And, I don't actually believe in the kid test because I don't think that's what drives, I don't think answers to kids is driving our answer. That's how we actually move our fields forward. I think there's a lot of things that we can't answer to kids that are actually pushing the edges of what humans are able to do as a community. But that, and ride the bike is an example of that. So I don't think that may be a good goal to keep in mind, but you might be, as Josh said, you might have to be disappointed and live with that. But I don't fundamentally disagree with the goal of trying to have more insight, but maybe that isn't the thing to get obsessed about, is what I'm trying to say. And what Sam said about there are levels of insight, they're just not the ones wanted. Right, and that deep nets have their own.
But I mean, again, as people like
Right.
philosophers who've studied what makes a good explanation, or Tanya Lombroso, who studied these questions in cognitive science, have argued that, for example, if you can, explanations, like Tanya has this paper on explanation as export. I mean, it's an old paper, but the idea that if we have two models, one of which just makes good predictions, right? But another of which it makes some predictions, and we understand some principles of how it makes those predictions that would allow us, for example, to map those insights. Those are the insights that would allow us to
Make
build
different
similar,
predictions
well,
about
either
something
make
else,
different,
yeah.
say how the model would work on other things, or tell us which other domains that model would work for and which ones it wouldn't work for, right?
Ptolemaic epicycles
In virtue
can't
of
be
what?
transferred.
Does this model
yeah,
work?
right.
Apples,
So
right?
because then we would say we have a better understanding, or we've better explained in this case than in that case. And I
Okay,
think
so
we'd
then
all probably
taking that
agree with
idea,
that, right?
what are those
Well,
things?
the
in the case
architecture,
of
the things that, I mean, again, I've heard both Jim and Talia and Sam all say some versions of this. Like, for example, if somebody says, well, like actually, at one of our CBMM events, one of our colleagues from Hebrew U, I think it was Shai Shalev, said he had been playing around. He's not a deep learning person by training, but he's a just general machine learning person, and he'd been a wide range of network architectures for many different problems, including with Amnon Shashua at Mobileye and in various settings. And he said, and I took this as a very sober, not partisan assessment of the strengths of deep learning. He said, Where deep learning really shines compared to other techniques is where you have some kind of repeated structure in space or time. So convnets capture repeated structure in space, which is very important in images, and like you guys had success in auditory scenes in that way to some extent, or like recurrent nets capture repeated structure in time. And so they're basically like the patterns of weight sharing that you get when you replicate things across different scales of space, or effectively recurrent nets share weights across time, or because you can think of it as just like you can unroll it into a deep network in time. That those are places where neural nets really shine. And if you don't have that kind of a setting, then just probably other pattern recognition techniques, other machine learning techniques will work about as well. Now, I don't know if that's true or not. It sounds like a reasonable generalization.
It sounds like a principle.
It sounds
like something almost like an
It sounds
understanding.
like you understood something. Yeah.
Like
And you might, I'm looking over there at Sasha and Tommy. You guys maybe even have some theorems that kind of go along with it. They're like some of the work that Tommy's done on compositionality, some of the stuff you guys. So feel free to weigh in if you want to. But I think those are examples of principal insights into classes of architectures and classes of problems that might also make sense. Like the brain cares a lot about things where there's repeated structure in space and time, so that might make sense.
But it also helps understand what are the things that are not going to be well captured.
Like
yes.
certain.
And maybe Talia's question of what exactly are the features that discriminate these categories. That's a good example of something where you might be disappointed, right? Because
Those
maybe
don't have labels.
we
Or
don't
neural nets might not
know,
be.
we don't know beforehand how compressible a mechanism is going to be, right? Ideally, it's going to be super compressible, and we're going to have the summary of it with very few parameters, and that's the most satisfying. But it could be that that's just not possible, right? And the history of artificial intelligence, I think, has shown that these very general solutions usually have exponential time complexity, and what it requires is a lot of knowledge about the world, and we don't necessarily expect that to be extremely compressible, right? So if object recognition requires you to know a lot about what stuff looks like, right, maybe that's not infinitely compressible, right? And that's just got to be in the parameters. So therefore, I think this argument that we want to, no one here, but in vision science and other parts of neuroscience, many people feel you should have models with a handful of parameters, right? Which probably we all think is crazy, right? But we have to accept that it's going to be high parametric models.
Yeah, I mean, again, I think it depends really where you're working. Like to inject kind of a higher level cognitive science perspective, which might make contact with some of the folks at the other end of the room over there. I think work in cognitive development, like thinking some of Liz Spelke's work, does a very good job of characterizing in very concise, high-level, but very precise ways also. What is an object, for example? Like to a young baby, to a 3-month-old, there's a concept, before they can tell the difference particularly between dogs and cats, right, or trucks and buses, there's this concept that's sometimes called the Spelke object concept, right, which is just, a chunk of matter that moves coherently through space and time, that doesn't teleport, that doesn't wink in and out of existence, that moves smoothly and together through space and time. That's not a totally precise definition, but it's pretty close. You can turn it into math, and you can use that in principle to parse the world into objects as young babies do. Or like the difference between animate and inanimate, right? I mean, you might say something like, entities which cause their own motion. That's more or less the difference between animate and inanimate, almost literally, right? And intentional agents are ones that cause their own motion where there's some goal and some kind of efficient planning with the principle of efficiency. This is a notion of an intentional agent that in some form, even 3-month-olds seem to be sensitive to, and in more sophisticated ways, 9, 10, 12-month-olds are very clearly sensitive to. So that, I'm interested in that aspect of concepts. I think they are grounded in perception because we can see things, and yet I'd love to see how to get, let's say, neural networks to be sensitive to that kind of concise, abstract, conceptual understanding that can also ground out in perception.
So maybe let's talk more pragmatically about how to go about this, right? So for example, this would suggest to me that you should be developing tasks that we can use in my lab to train neural networks, right? And to do experiments maybe with animals.
Yeah, we are.
As well.
That's why I'm part of CBMM.
So I think
So like some of the tasks which I
want
hope you
to
saw today.
So I think
yeah.
I want to sort of think of the frustration. How can we channel the frustrations into something that helps the community?
Yeah.
So
right?
I think that
So the frustration could be, yeah, these models do the task, but they're not really like brains. Well, then, define a test that would make you accept that they are like brains, right? Then you can measure how they fall short, and then someone else can build a better model and measure according to your criterion, right?
I think, I mean, I'm not really a vision scientist, but I've read plenty of vision science, and one of the things that I find frustrating about the current zeitgeist around deep learning models of vision is that Josh mentioned this earlier, basically it's a very impoverished notion of vision, what our visual capacities are, that vision is doing a lot more than just object recognition. And I think, and so just practically speaking, I think that there's a whole wealth of scientific knowledge, studies about vision that the people doing deep learning should really be attended to. So as a starting point, for example, Irving Rock's book, The Logic of Perception, is a great place to start, where he really thinks about perception as problem solving, and he has it's an old book. By the time he wrote that, there were many, many examples of very non-trivial kinds of surprising aspects of visual cognition that to him and to me also feel like more like problem solving than some kind of...
Are there good examples that like come
So
to
actually,
mind?
so one, I suppose this isn't really a ventral visual stream, but I remember talking to Tate Adelson a number of years ago when I was here and I told him I was interested in motion perception and understanding hierarchical motion perception. I was building models of that, and he pointed me actually to Josh's PhD studies, and he said that he basically he thought that if I wanted to study motion perception, I should really be building models of those studies, and the reason was that Josh basically did I don't know how many dozens of experiments with these moving lines behind occluders, and Ted basically expressed the sentiment that he kind of gave up on. I don't know, Josh, maybe you can opine on this, but he basically expressed the sentiment that he gave up on trying to build computational models of these phenomena because it's like every kind of new thing that they threw at the visual system, it's like the visual system could come up with a clever solution to it, but he could never find some very simple model that explained why. And I think that speaks to this idea of perception as problem solving, that our visual system is somehow very clever at coming up with these solutions to these weird stimuli, often in terms of objects occluding other objects and moving in particular patterns, and a lot of that I think is missing from.
So what would the task be? Can you give an example of a task and what the response is?
So I mean, I think as a start, we should really be paying attention to Liz Spelke's experiments. I think that should be the starting point of any investigation. How do you get neural networks to perceive objects in the way that human infants perceive objects?
I think that
doesn't seem intractable.
No, I don't think it's intractable at all. I think that they're just not paying attention to it. Yeah.
But I mean, to be fair, I mean, this hasn't necessarily made its way into human perception, but there are people in computer vision that are returning to some of those problems, right?
Yeah. So there's lots.
It's not just object recognition anymore. In computer
vision. No, I totally understand that, and I want that to filter back into neuroscience and psychology. Yeah.
I agree.
Another example is this task that Max over here and Ilker have worked on, and others in our group. Which did you show him the cloth task? Oh, okay. All right. Well, but you guys could maybe imagine this if you haven't seen this. But so we've been studying these problems where, let's say, for example, an object, like could be a familiar object like a chair or just some shape. And then I'm going to show you the same object, but kind of draped under cloth. Again, like this was inspired by some demos and studies that Ted Adelson and some of his students like Philip Isola did. And people are surprisingly good at being able to recognize what is the 3D shape of the cloth. The cloth has to kind of be sort of thin and silk-like so that it really reveals some aspects of the object shape. And you can show people like, here's a chair, and now I'm going to show you two slightly different chairs draped under the cloth, and you tell me which one it is. Or here's a car and two slightly different cars. Not perfect, but you're very well above chance. And we can compare to various kinds of deep networks. And I think for the hard problems, what we've found is that at least standard deep networks are are not above chance in cases where people are above chance. And it seems like people are doing something more like a 3D interpretation and a kind of problem solving in the sense that you're basically trying to say, well, something under that cloth, what is it, right? The cloth preserves some of the contour type features that are diagnostic of images. So in easier cases, like if I say, can you tell whether it's a chair or a table under the cloth, or a chair or a computer? Yeah, so like easier things, the deep networks can do pretty well at, right? But these subtle details, which again, it feels like a kind of unconscious problem solving. Yeah. And we're interested in that because, for a number of reasons, but one reason is that, it shouldn't be that hard. Like, we should be able to train deep networks to do it. I don't know, have you guys gotten that to work yet? Like, we're working on that, and then we can ask, what would it take to get deep networks to be able to do this? And is that, does that say anything about what might be going on in the brain? Another is that, it turns out even babies can do this, right? So René Bayerjean, I think, did these experiments. Who was it, Bayerjean? Yeah. Showed again that basically infants are sensitive. Like if they see a cloth draped over something that, would otherwise, if there weren't an object there, the cloth should be flattening down to the floor, but it kind of doesn't do that. Then they infer there's an object behind there. Yeah. These are examples of I think, some ways to tackle these problems that would be nice challenge problems. I say, could we get monkeys to this? Could we study this in the brain? It's not crazy that we could do that. Yeah. I think it'd make some progress for us.
Yeah, I think this gets us to our other big obsession, discriminative versus generative inference, right? And I think that's a great topic, and I'm struggling with it because I totally agree with you. It's hard to see how a feed-forward deep net can model this. Even if it can do the task, you can come up with versions of this task that it won't be able to do, and to the extent that it can, it's not doing it the way that we do it, right? I totally share that intuition, from the introspection of how you look at it, the conscious thoughts that you have while you're looking at the cloth, and I totally agree with that. And at the same time, it's very intriguing how can we model what's going on in our brains, right? So I've heard earlier today people in your lab working from the top down with physics simulation and adding some noise to the physics simulation, and that's exactly the complementary element, right? But at the same time, I feel that's also not how the brain does it, right? I feel that we need both of these. I mean, we need to work from there on down, but I feel what the brain does is a seamless integration at all levels and along multiple levels of redescription of the input of discriminative and generative.
Sorry, Niko, are you equating don't understand discriminative and feed-forward?
Yes.
I wouldn't. I mean,
okay.
But maybe you're using the terminology differently.
Okay. Well, for example,
So there's a machine learning definition of the distinction between discriminative and generative, where the discriminative model is modeling conditional distribution, like conditional distribution over object labels given the
Okay.
And that could be anything, right? It doesn't have to be a feed-forward neural network. It could have recurrence and all that sort of stuff.
That's true. Yeah, maybe I'm not.
But anyway,
like
I think I would agree.
Field, for example, or something.
So what I mean by discriminative is mapping from the input feed forward to some variables of interest, right? So maybe let's recount, maybe that's useful, what's good about that, and then what's bad about that, and then we can do the same for the generative approach, right? Yeah. So I would say for feed-forward mapping, what's good about it? Well, it's fast, it's rapid, it gives you variables of interest that are useful for behavior, relevant to the behavior. It's relatively easy to train with supervision or also reinforcement. It's quite straightforward in many ways. These models explain, representations and some aspects of behavior, right? So that's what's good about it. Maybe one other thing is good about it, which is if the generative model that we're trying to invert as linear with Gaussian noise, then it's actually the optimal thing to do. And that brings us to what's bad about it, which is that when the generative process, as is almost always the case, is more complicated, then it's statistically not the right thing to do, right? And it's going to be an approach to some extent or a compromise to some extent.
Are you making a statement about the sample complexity, like how much data you need to make an accurate prediction, or? Or what do you mean when you say statistically it's not the
Yeah.
right thing to do?
Yeah,
Because
one
there
more
are
time.
theoretical
You guys
results
agree
that
with
show
that?
that at least for certain classes of generative discriminative pairs that actually sample complexity is better for generative models, but they achieve lower asymptotic. They achieve higher asymptotic error than discriminative models. But I think maybe you're drawing a different distinction, so I just want to understand that better.
I guess I think the biggest difference of following up on that is for a generative model, or I mean, discriminative model, you're learning to predict or draw from a certain conditional distribution, which represents a task, basically. And machine learning is pretty much always oriented around tasks. What's the task? Or we're doing this task or that task. But to me, the biggest, or one of the big reasons to be interested in generative models in the brain is because there isn't just one task, right? We have, this almost the essence of the cognitive science approach, our ability to build models of the world. Sometimes there's no, the ability to build models of the world which we can deploy either for no task or because we're just walking around and curious about things, but or to deploy for a new task that we hadn't ever been trained on at least, or even, it didn't even exist until somebody introduced us to it a moment ago, right? So like that game you showed me just last night. I mean, games are one place where, here's a new task. I explain to you what you do and you start doing it. But it's not just in games, it's many other activities. And it seems like, it's not clear where that comes up in perception, but it's one of the reasons why we've been interested in things that, sometimes we call physical problem solving, places where your understanding of physical objects and intuitive physics link up with, new problems that you have to solve that you really just, have not had experience that would make it a traditional task from a machine learning perspective. Yet somehow our perceptual system gives us the knowledge which we can act on and plan with to solve this new task.
So I agree completely, but I feel compelled to state the counter argument, which is that there's often lots of generalization to other tasks. Once you train up a simple classifier on some representation you've learned for a particular task, right? So.
Well, right, but we should distinguish between generalizable representations that can be relatively efficiently retrained for another task, right? Say something like, the now standard thing that you train up a deep network on ImageNet or Places or something, and then you have some high-level features which can be quickly reused for another task. But still, typically, that requires some amount of retraining. Right?
I agree. Yeah, of course, I agree completely.
Saves you.
But I also state that, also counter argument, you say there's no task, there's always a task, survive and reproduce, right? And I think this comes back to what Niko said is like, AI is going to task drive to survive and reproduce eventually. And what we should be doing if we want to be in the game, actually picking tasks and using data, as Niko said, to constrain things and not tell them they're on the wrong course, because it's just going to go, right? And like our job at someday, if we just sit back long enough, we could imagine, 50 years, 100 years from now, our job will be to just take whatever existing AI algorithms are on the shelf to say, which of these is actually in our head? And that would still be a useful endeavor. And that would, that wouldn't be a bad thing to do, because
as in many other parts of science, where
this is already how we do our science.
And that's not a bad thing to do. The question is, can we accelerate progress by doing more than that, by actually engaging in the task now and not
in our
being
lab, that is
part
what
of
we do. So I think we should all do. You do that too.
I know. I think the spirit, we'd all have the spirit like to do that, but in practice, what Niko's saying very important is came up at the CCN conference when we had Nancy and you there, and I said, we don't actually agree on what our goal is. And Nancy, I will never forget your reply, which is like, I think it's okay that we don't agree what the goal is. And I think that is actually part of the problem. We need to pick some goals. We need to pick some.
We're allowed to disagree about that.
I still disagree about that.
We need to pick some goals and work towards them, because as little isolated islands, with our own idiosyncrasies, we won't
If
actually
we all
achieve
pick the
it.
same goal, we'll all make the same
We
mistakes.
don't have to all pick the same goal, but at least some shared goals. That's how you're going to progress as a community. That's all I'm saying. I think that's what Niko's trying to say with the task too. And I think you're saying you have ideas, and how do we actually
Well,
make
again,
this happen?
at the risk of just sort of saying the same thing a couple of times now, one of the reasons why we like these physical problem-solving things is because these are tasks like, how do I see this object and see what I can do with it, or use, for example, we have these tools.
Trials of behavioral data you collected. Where do I download them? That's what that's what we have to do. It's not just kind of
give me the website. But let me just finish. What I'm trying to say is these are examples of tasks that push beyond what currently we understand how to do in neural networks and tap into something. On the one hand, there's ability. We're saying, here's a new thing, you haven't done this before, use this. But these are the kinds of things which our ancestors, evolution, I think, are, we can all tell evolutionary stories, but if we were going to tell a story, the idea that our brains were distinctively shaped for flexible tool use, for example, as well as our ability to understand how tools work and explain them and pass them on to others and develop those culturally. That's one of the many reasons to be interested in certain kinds of these kinds of tasks, because they have flexibility, but they are directly related to our ability to survive and reproduce. And they directly ground in perception, but they also have to be things that we have to be able to converge on and talk about. So I'm just saying these are, I think it's important to think about all these considerations. I also agree with Nancy, we don't all have to work on the same thing, but it is helpful to have, particularly if we're trying to cross the different levels, right? If we're trying to cross brains, minds, machines, and AI and engineering and all that, we do need to have some shared tasks that, that in particular you and I can all buy into, or find value.
So, I mean, one other thing that seems worth mentioning, which we were talking about last night, is that, I mean, there is a very real and likely chance that, let's suppose that what you're suggesting actually transpires, right? And there's all these systems, and we're trying to figure out which one maps onto us. I mean, there's lots of people who would find those models totally inadequate, right? I mean, if you want to build a brain implant or understand how the system malfunctions, I mean, you might actually need to have neurons in your model, right? So there's a whole issue of the level at which you're modeling things, which depending on what you want to do could end up being totally critical. And a deep network.
You might even need a flexible generative system to figure out how to adapt to new goals or something like that.
Yeah.
Or not.
But I mean, someone who's interested in translation is not going to find these models very useful, right?
Yeah.
So,
There's a question.
Actually, I have a comment regarding the adaptability of deep networks. So, one of the problems that you train a deep net for a large set of, let's say, space images, and it does very well in classifying them. And you take the same network to retrain it for a large set of face images, again, very rare, but it forgets the previously learned label. So it looks like it's not that much adaptable. And that is kind of opposite of human visual system, because we can learn new things without forgetting the previously learned things.
That's because we do it in two different networks.
Yeah, it's actually more complicated.
Maybe that's why we have different sets of networks, so you can learn a bunch of faces and not forget all your scenes.
So unless you think of it as kind of separate modules, but if you're going to use the same network for multiple tasks, it doesn't have a notion of long-term memory. It forgets the previous labels.
So is this supposed to be another one of the arguments against against deep network view of the brain? Yeah.
There's just a single time scale of learning, essentially.
Yeah, or treating the whole brain as one big deep network doesn't seem plausible. But I don't think anybody seriously thinks that's true, right? For example, the complementary learning systems ideas. Right? I think these are ideas which, for example, at DeepMind, building on earlier work from Jay McClelland and Randy O'Reilly and others, people have been exploring ways of solving this kind of problem, right? Not fully satisfactorily yet, but I think nobody who takes the toolkit seriously as a tool for understanding the brain thinks the entire brain is one big deep network, even the ventral street.
Which I think is a very interesting potential use of deep nets, is to try to understand why we have the modular structure we do in human brains, right? It would be very cool if that emerged from.
A little bit more general question. I would like to pose the question to the panel. To what extent generative models and discriminative models are mutually exclusive? What do you think? Could a brain host both of them and have interactions?
Absolutely,
of course. Yes. But you can always derive from any generative model. You can always derive a discriminative model, right? By conditioning, right? But you can't derive a generative model from a discriminative model. And I think this kind of speaks to what Josh's point earlier, which is the difference in flexibility of those two approaches. If you train a conditional distribution, you can only radically restricts the kinds of queries that you can answer about the world. But if you train a generative model, now you have more flexibility because, at least depending on how you design it.
Can they coexist?
Yes, yeah. I mean, and there's good examples of architecture. I mean, the one classic example that inspires a lot of us is the Helmholtz machine. So this idea from Jeff Hinton and colleagues in the mid-90s, right, where a generative model and a both implemented as a neural network with the same topology, but just the arrows going in opposite directions mutually train each other. And it's it's in some ways led to what we now call variational autoencoders. Some of the models that we've been building in our group have a similar character, but where the generative model isn't expressed as a neural network, but something like a graphics engine. But you might use a neural network that learns a recognition model for a probabilistic graphics program. But many people are exploring versions of this kind of idea, and I think it's very interesting, and it's also interesting to see whether that might have something to do with, give us some insights into what's going on in the brain. A lot of us
I think
nod to this. We
all
want
of
to
this
figure out how to
is-
make progress on that.
Yeah, exactly. I think that's where the action
Yes,
is, and
yeah.
I'm fascinated by how to integrate. Let's not call them discriminative
Yeah,
models, but
yeah.
feed-forward computation
Yeah.
and inference on generative models that probably requires iterative recommendations of some form. And so, how do we think about that, right? So there's one thing that is perhaps, from my perspective, ultimately gonna have to be questioned about this statistically beautiful approach of specifying the generative model and doing inference on it. And that's the fact that it is perfect when we really are able to encode all our knowledge and all our uncertainty and not leave out anything that we haven't formally eliminated, any possibility of the generative process, right? Then it's perfect. But in reality, that's almost never possible. So there's always some degree of model misspecification. And it's going to be very hard to learn the generative model explicitly, right? So when we describe the system, in engineering, it's beautiful to have the model separate from the algorithm, right?
Yeah.
It's just sort of, it's a neat way of thinking about it. It's a good way of understanding it. But when a system like a brain just learns how to do the task, it doesn't necessarily maintain that clean distinction, would be my intuition on it. And it's going to cut corners. It's not going to keep these separate.
Yeah.
It's going to make many compromises and combine feed-forward computation and some iterative inference, and maybe at a high level where it's computationally more tractable, it's going to do simulation and understand causality to some extent.
Yeah, no, I disagree with that, but I guess I would say that it's one of the reasons why we're very inspired by video game engines, because increasingly video game engines have graphics engines that are near photorealistic in most of the ways that count for people, right? Not necessarily fully photorealistic, but it's increasingly the case that you can quite a lot of the relevant part of the generative model that has to do with how light reflects off of surfaces, spreads in the environment, and how off different kinds of surfaces it renders quickly into what we see. So the idea that the generative model that we might be inverting is really especially the graphics engine. It seems quite plausible now that we can, it's possible to build generative models that capture almost everything that matters, right? That still leaves open, for example, how you would learn what kind of objects are in your world, right? Or how you might learn to deal with weird kinds of lighting conditions that are not already there in the generative model. And that's, to us, that raises the question of learning more things that are more like structural learning, like learning programs, right? So some of the work in our group is about learning graphics programs, where we might mean like generative programs for objects, for example, with that when you combine those with a renderer that describes how light bounces off, so you might get a fairly complete model for scene understanding.
So I love that metaphor of the game engine in your head, because the game engine has to be a compromise also. And
Yeah,
it has
exactly.
to be
It
online.
makes all
it
the
has
same
to
kind
be
of
real
compromises.
time.
Right, exactly.
It has to make all of these
Yes,
compromises.
that's right.
Nevertheless, I don't think that predicts down to pixels as a game engine does, right? And I think, on 20 watts, I don't think that's going to work down to that level, right?
But that's a great
nothing
inference
works on
question.
20.
You
Well,
have to ask that
really,
question.
it's
To
a
what
really, it's a
detail?
really good question,
Yeah.
because at least when I see a lot of reasons to be skeptical of that, and sometimes I am, like the day I am, but for the times of the day when I'm dreaming, dreams are, people differ on this, but for many people, and for me, dreams can be incredibly vivid in the detail of the imagery.
And why does that matter?
But because they feel vivid,
It doesn't
doesn't
necessarily
mean
map
you're
to
filling in
pixels.
each
It
pixel.
doesn't map to
yeah.
pixels. Whatever it maps, it doesn't necessarily mean it maps to pixels, but it maps down to the kind of level that mean, game engines are only interested in pixels at the very end, right? Mostly they're interested in how light bounces off surfaces from the viewpoint of the player, right?
Yeah, and Niko, I think it's important to separate thinking about the game engine as a generative model and thinking about the inferential computations that are necessary to do inference in that generative model. So you could have a generative model that predicts down to pixels, but that doesn't necessarily tie you to defining an inference algorithm that operates at the level of pixels. So you can, so for example, there's classes of algorithms that use summary statistics on both the actual images and the images generated by the generative model and compare them in terms of summary statistics. So that's just one possibility in this space. Right? Talia, were you going to say something?
I was, but I don't know if it's a good idea, so it might reveal some
That doesn't stop the rest of us.
I was thinking about the primitives of the two modeling approaches. So deep nets are working off of pixels, and it strikes me, though I'm not an expert in this, the higher level models often operate at higher level primitives. Like I'll work over, do inference over objects. I'll just grant that there are objects, that there are entities. Number of them, like there's a lot of structure that's implicit in even the primitives of these high-level cognitive models. And it seems like maybe there's a useful way, like what are the primitives that some of your most successful high-level models need? Like maybe deep nets can get us there from the pixels.
Yeah,
like that's the joint.
Yeah.
So if you just say,
Yes.
here
Yes.
are the things that my models need.
Yeah.
I don't want to solve to the
Yeah.
pixels.
Ex-
That's
yeah.
a lot of work. I got shortcuts for that
Yeah.
deep nets can just do because the representation of the world has not changed that much and I can learn it pretty efficiently with
Yeah.
the simple algorithms. And then those
Yeah.
get you to the, so you're not trying to make it generative all the way down or deep net all the way up. Like
Yes.
the
So, I mean,
joint has got to
I
be
think that's-
probably
yeah.
right where your primitives are. on
Right
this
where
higher
like
level.
Spelke and Barjan and others have
I
identified.
think
Well,
that,
for
right, that-
infants, but I think for adults, maybe like object categories
Yeah,
and their
that's right.
locations.
Fair
And
enough, fair
then
enough.
on top of that,
Yeah.
you have all this kind of higher level stuff where you see the physics of the world and the social structures and all this other stuff that's relational and maybe not
But
so.
but I mean, just as an example, so some folks in our group, like for example, Jiajun Wu has a couple of papers that he's published recently at CVPR and it will present later this year at NIPS, which do very simple versions of that. He calls them neural scene derenderers, or there's a neural physics deanimation, this is NIPS paper, with a number of colleagues. But basically, yeah, a neural network is trained to de-render a graphics engine, basically to pick out the objects and their properties and locations, which are then exactly the things that you would have as input to a physics engine. So it allows you to like look at a scene of blocks and very quickly, very, very quickly pick out the relevant objects and their physical properties that are needed to then imagine what's going to happen next via your physics engine. And it's that kind of, again, why it comes back to Liz-Spelke, this sort of 3D, in this case, 3D solid objects, Spelke objects, that is the intermediate substrate. It's the thing that the physics engine operates on, but it also is a natural target for the bottom-up pass.
So instead of categorization, the model could do roughly like what are the like weight,
Pick out
maybe
yeah.
like a few
Yeah.
surface or critical physical
Exactly, yeah. That's kind of
quantities
the
that
idea.
enter into physics. Like
Yeah.
that's a task. It's a
Yes.
very specific task.
Yeah,
We
and,
use
and
training
Nancy
data,
and
but that's
Sarah
something that we
Sweatman
just
and
do.
Nancy's lab have been that might actually work in the human brain, basically.
Another question.
Just kind of hop off that. If you're granting that this set of visual primitives is the point at which some of these higher cognitive engines start, that's a lot of primitives that you get. So if you take the game engine analogy, for example, bounciness is a primitive in a game engine, right? That's a pretty sophisticated primitive when we're talking about it. So if you're granting that you get this whole set of primitives that your engine can then start with, and you're granting that a deep net can do a whole lot with a very little amount.
I buy that. I
Yeah.
think the vision could do that.
But we have to be careful about what we think are the kind of derived primitives and the more core physical primitives, right? So we may perceive a quantity that's bounciness, right? But at the level of specifying the underlying physics, it might matter more about like the material elasticity and its mass and so on, right? So there's like an innumerable number of physical properties. One layer of abstraction away from.
And wonderfully,
Yeah.
these are
Yeah.
empirical questions,
Yeah.
right? You can ask both
Yeah.
kind of perceptually and
Yeah.
with neuroimaging, which of these things do you encode and how
Yeah.
precisely and how automatically?
Yeah. And that could be a place where neuroscience could help to guide the AI stuff.
Absolutely.
Because it might say, right, like what are the actual key properties which is why.
Right, well, so Sarah's
excited,
looking at
yeah,
this,
and
right?
so- exactly.
So Sarah's shown regions of the brain where you can decode the mass of an object generalized across the scenarios that depict that mass. And so the cool thing about that is because it's neuroimaging, we don't need to ask the subjects, okay, what is the mass? We can just scan them while they look at this stuff, and we can ask under different task conditions, when do they encode the mass? Because we can read it out and see.
Is it in the visual system?
It's like
Have you
private,
checked
frontal, it's all kinds of weird, disreputable locations.
Oh.
Make me very nervous. Yeah, Layla.
I guess I have a question mostly for Jim, which is what you think beyond object categorization, the tasks we should all be standardizing are, and is it the same level of standardization that like computer vision has for ImageNet that you think we need?
Just two questions. One is the type of task, and the second is like, how do we actually maybe get it done, right? Because I think that's something the computer vision community has done that I think our community would benefit from too, and I keep trying to start some version of that in my lab, and Niko and I have talked about that. It's just hard to get the infrastructure in place to.
That level is what.
Well, when you say that level, what does that have? It was like at least there was an agreement, like here's a problem that people were all working on, and then there were measures of progress and so forth, right? And so that, among many problems, is what I imagine. And I actually don't care what the problems are. And I think us obsessing too much about what the perfect problem is frankly a problem itself. It doesn't like spend all that energy to actually put the things together. And that's why when Josh is saying, I need this, I'm like, give me the million tries and thing, and like, I'm happy. I don't actually care. But if you had to guess my guess, I would think about things that are like slightly beyond vision. We all have our own intuitions about that, and like other estimates of properties. You guys have talked about them. And again, the more the better, right? I don't think there's a right answer to these things. It's just about being efficient. I mean, this is an engineering problem. This is not an overthink it problem. This is like human genome kind of stuff here, right? This is a complicated thing that does many things. We're not going to think our way out of the box, right? Just do it is sort of what
I don't know. I mean, you can get into you can get yourself into a lot of boxes, Jim. I mean, there's a lot of boxes that get stuck in, just like computer vision got stuck in a lot of boxes.
I know that's provocative, but that's kind of.
Well, computer vision got stuck in many boxes by in some sense, prematurely defining certain kinds of benchmarks.
Including the ImageNet. So Fei-Fei Li, who created ImageNet.
Now you're saying they got stuck because of ImageNet?
Yes. Well, Fei-Fei Li said, I'm not saying that Fei-Fei says that. Fei-Fei said.
Well, now they're stuck, but it was not stuck for a while.
Yeah,
I mean,
that's right.
So you've got to do it, and then you make progress.
There's always another layer of.
I want to hear what Fei-Fei says, Josh.
Well, Fei-Fei has said, and she's very much of an advocate for the kind of approach you're talking about, but she's also said that I don't want to exactly put words in her mouth or try to remember exactly what she said, but something like ImageNet killed computer vision. She didn't mean it in a good way. Because I think,
by getting people to focus too narrowly.
Too narrowly. She created ImageNet, and she's also created a bunch of other data sets, like the visual genome, and then recently she's been working with this clever data set. And for the most part, people just keep using ImageNet, and they also use places like lab, for example. There's a small number of data sets that, like in anything else, just like there's a small number of architectures which many people have used and continue to benchmark against, and that's good in certain ways, but it can also limit progress. I think Fei-Fei was saying this.
Do you agree with that?
Do I agree with what?
What Fei-Fei said? I'm just
Did it kill computer vision? Well, I mean, I think it had pros and cons. Certainly, I mean, she also meant, I mean, just like what Jim said, like it certainly really drove a lot of computer vision progress for a little while. Yeah. But the issue of
kill field doesn't that mean it's done? Or
no, well, I don't think
that's not what she means.
I think the thing is that I would side with Nancy. Like, you need a little bit of chaos in your field, because if you have no chaos, then everyone is going to optimize this one thing that we all agree to optimize, and then we might not even be able to burst out of that box and realize that wasn't really the thing that we wanted to optimize.
I agree that you need some balance, right? You have everybody working on one problem, that's a mistake. Yeah. But don't you maybe think that there's a possibility that the whole field of brain and cognitive sciences, broadly speaking, is right now a bunch of tiny little islands going in a bunch of tiny little different directions, and that's a better description of our field than we're after the one thing.
Exactly.
I mean, which end are we more close to? And all I'm trying to do is put a little bit of force.
That's fine. I'm with you there.
Yeah. At the moment, neuroscience, systems neuroscience is like you start a project, and that defines a game which you then play and claim you won in the paper, right? I mean, is there anything wrong
Well,
with
that's
this?
kind of like a lot of
It's a
computer
little
vision.
bit, there's a bit of a problem, right? And so this is
That's for
this
kind
is
of
the-
political reasons. So
I
you
mean,
need
the-
to make, yeah.
Yeah, I mean, there's
That's what I'm saying.
there's a beauty to it, and we love it to some extent. It's the cottage industry style of systems neuroscience, but now it's getting a bigger, right? So we want these big models, and not everyone is comfortable building
And you want more
training
people to
them.
play the same game? Is
And
that
we
the idea?
want data, and we want bigger data. Everyone agrees we don't have enough power, so we want maybe we want 100 subjects or something like that, and we want statistical. And we have to invent some of that, right? So for any one lab, that's a little bit difficult. So we have to go beyond the single lab, cottage industry, single study approach, right? So we
Where
have to
each
share a
study
little
invents
bit
its own
more.
game. Is that
we have
is
to
that the
share a
sense?
little
Yeah.
bit more,
Yeah.
and that's
Yeah.
why I think the
Yeah.
productive thing to channel the frustration is build a task, share it,
Yeah.
and that's like an offering.
Yeah,
So
and that's how it
here's
works in
my
computer vision. Yeah.
criterion.
Yeah,
for
good. So I mean, at its best, that is how the computer vision community advances things. Many innovative papers will define a new domain data set task and then share it, and that's. I think if we had that as our collective value, then people will self-organize around interesting tasks. Yeah. Are there more comments? Did we get to all the things you wanted to get
This
to?
one in the back. Ethan, yeah.
So, I guess, paraphrase this. So I feel like, let's say in chemistry, we have the periodic table, and we feel like we kind of understand what's going on, and like we kind of believe that table. And like when we created that, there was like a hole in it, and there were like predictions that this thing was missing. It's kind of a model we believe. Like
Yeah.
we're in neuroscience, if I said, does the brain work like a neural network, I wouldn't have a lot of confidence saying it really does. Like maybe that's just me, but I mean, how do we know when we have kind of the right model? So like we create a lot of kind of systems where, okay, these neurons kind of look like neural network neurons. It maybe explains 50% of the variance. But when are we going to get to the point where we can be like, oh yeah, that's kind of right? Does that make sense? Do you feel like neural networks really are explaining how the brain works, or are we explaining ant brain vision?
Or like the fact that like Jim will say, well, we've explained 50% of the variance in the ventral stream responses. Does that mean we really have understood 50% of the system? Is that what you're asking about?
Yeah, or have you understood anything? I mean, because if you're taking a network that's optimized to work like humans, presumably it's going to look something like humans in some of the responses. But how do we know, like, are neural networks really a good model? I mean, people weren't using them very much before AlexNet. So I don't know. I mean, how do we know when we're right, kind of, or have some confidence in that?
Well, I think we're very far from, obviously solving how the brain works. When you say neural nets, that's a little bit amorphous, right? So where does it end? Where does that framework end? Does that include spiking neural networks? Does that include everything we can do with recurrent, arbitrarily complex? I mean, I think that's a very rich framework that's probably going to serve us for quite a while, right? And that I can imagine could suffice, if it's got enough units and is extended in the right ways to cover sort of the critical things about the dynamics in biological neural nets, right? It's a bit funny when you say, okay, is the brain, can it be explained by neural nets? It is a neural net, right? So obviously, yes, right? If you define it right.
Wait, what are the critical things? Do we know what the critical things are?
No, we don't.
Okay.
Yeah, so it's an empirical question. We have to bring these.
Wait, is it an empirical question? What the critical things are?
I think
that
it
You
is.
can mess with your net and remove various
Well,
properties
you're
from it,
using the
essentially.
word critical in the sense critical for a certain task, right? But not critical in the sense that these are the things. I think what Ethan is asking about is what are the things that we need to explain, such that once we've explained them, we can declare victory. And that doesn't seem like an empirical question at all.
When if you look at other fields of science, I don't think you would say any field has answers to that. It's just when it delivers products along the way of various forms, right? And then that's where the that's where the payoff is.
And
those
you can answer toddlers' questions.
and about string theory. I mean, you can't always answer.
The universe looks like it's made of things, but it's actually made of these little tiny vibrating strings.
There's a
They're little circles.
there's a lot of progress in fields that still
Yeah.
It doesn't have to answer Taler's questions to actually have payoffs in certain
True,
use,
I agree.
right?
I agree with that.
And I like share Ethan's goal of like defining the end because that motivates the kind of here's the thing we're all on. But you know, along the way, there's going to be various successes that are different levels of abstraction. Different parts are going to come in depending on the models that we're using. I mean, we could start to maybe a good discussion would be guesses like what are the first things that we think would come out of progress. I mean, for me, it's like predicting humans' behavior is actually not that far away. Part of for the reasons Sam said, right?
Yeah.
That's not brain-machine interface yet because we don't have all the neural details. It's not curing disease yet because we don't have drugs to interact with the channels in the right way, right? There's like down to the levels of details in the models, but those are guesses of how I think those are going to. We all have our own guesses there.
And I think we're you know, I think part of the problem here, the reason why we don't have more consistency is that, and we saw this in this panel discussion, like, I don't know how many times Josh has talked about game engines and intuitive physics, and someone says, no, well, the brain can't do that, right? That doesn't look like anything we know what's happening in the brain. And likewise, a cognitive scientist might say, well, you know, these neural networks aren't doing the things that we think people do, right? And so there's a disagreement about, if you rule out the possibility that the brain is running a game engine in its head, right? Now you hit a roadblock, right? Because now you can't even speak to the same challenges.
But that's why I think that neural nets, and Niko said this in his talk yesterday at the beginning, that's why this is an exciting time because these instruments are touching both fields and they bring a common ground because neuroscientists can map them. They see units. When Josh says game engine, I'm like, and he used to talk, it's like, oh yeah, it's compiled somewhere, there's some transistors that are in neurons, but I don't know, that's like 3 levels down.
Yeah.
But we're talking about systems that now actually have units. They go, oh, those units look like the units we see. And if there's some interest on the cognitive side that these systems are doing something cognitively interesting, which is sort of what Niko was saying too, then okay, now we have a meeting ground. Both sides are unhappy, and I was going to say the attacks I get when I present this work. You know, there's the dualist attack, which is like it can't be. You know, the brain will never understand it. So we'll take that one but you'll hear that in every talk. The second one is the attack from above, which is you guys saying, well, it doesn't do enough of the task, it doesn't have a general model, and I get that. And then the one's from below. Wait, where's the spikes? Where are the channels, right? So, of course, it doesn't have that either. And then there's from the side, from the theory side, which I think is actually really interesting. We don't understand how it works, and that's important too, right? So all of those things are openings.
Jim, I'm sorry. I really like your work and appreciate it. I don't feel bad about it.
I'm saying this. I'm not trying.
They're challenges. They're trying to be open.
I'm just trying to say these are all the areas. But the thing I'm trying to say is that you're in the middle of all that, and you're trying to grow in all directions at once, and that's a good thing because now we're talking to each other, right? And so nobody's going to be completely happy. Is all I'm saying. So
let me just add like a little piece of historical anecdote, which is. Jim and I started teaching this grad level course on object recognition, I don't know when that was, more than 10 years ago. We taught it for a bunch of years. And I vividly remember when we first started talking to each other about what we would teach and stuff, I was like, well, object recognition, Jesus, we're never going to really understand that. So we'll kind of dance around the edges. We'll talk about how are things modulated by attention and, does mental imagery, like object, all these like side questions. And Jim was like, no, those are the side questions. We're going to understand object recognition. I was like, wow, maybe. But I kind of, it seemed kind of like totally out of the question to me at the time, not that long ago. And not that I think that project is done, but I think that, I don't know if you saw all this coming, Jim, but I sure as hell didn't, that we'd be anywhere near the level of understanding that, you guys, many of you, have come up with your ability to, show the mappings between, behavioral outputs and levels of, deep nets and the hierarchy in the ventral pathway. I mean, I think it's quite extraordinary. And, in recent times, that was really not, I don't think other people expected that to come around either. So I think we should declare like partial victory, at least. Victor's had his hand up for one second.
What I think, to point out something that I think gets perhaps, if not overlooked, then is only implicitly stated by the panel, is that understanding, whatever it means, comes in different levels of abstraction. And appreciation of these different levels of abstraction is something which can be very helpful here. And neural networks themselves, history of neural networks themselves is a perfect model system for it, because if you look, where do they come from? Well, it all starts, some would argue, with George Boole, right, who was trying to mathematize laws of thought, of human thought, in the most abstract possible way. And then century down the road, McCulloch and Pitts wrote this paper with a very cookie title, right, on, what was it, on logical calculus of ideas immanent in neural activity, right? Who here would right now think that this paper, it was very crazy at the time, right, mixing all these concepts. And then it took another 50 years to build those practical tools, which all illustrious panelists apply their everyday efforts. But it doesn't mean, and neural networks live their own life right now, but it doesn't mean that these more abstract levels do not exist and develop, and that they cannot provide understanding, perhaps not in the form of variance explained, but some deep insight, and they cannot provide unification, and they cannot provide some intellectually satisfying insight. I'm not afraid of that word. So I think that appreciating these many levels of abstraction and hierarchy of abstraction is something that we shouldn't be forgetting. I don't have much more to say.
Absolutely. I mean, I'd echo that, and maybe let's remember that we're talking about the same thing at two levels here, right? We're talking about how we need models and generative models of what the brain does, and in these models, there are models of the world, right? And in both of these multiple levels of abstraction, I think, are exactly the part of the big mystery, right? And potentially where measuring the brain and studying the representations in the brain can give us insight that might drive progress also in AI, right? And in addition, I hope that as we train more complex recurrent networks, that we can also see these representations at the higher level of abstraction emerge. And I expect that they might surprise us fundamentally, because they might be nothing like images, and they might be nothing like cultural products like language. They might be something really strange.
Maybe even
between.
Nothing like game engines?
Yeah.
Nothing
maybe,
like any of those things?
You know, maybe have some similarity. They might be analog, they're going to be dynamic, right? But at a very abstract level, and always just capturing sort of a little part of the dynamics and exactly what matters, and sort of dynamically dropping things.
Maybe that's a good note to wrap up on. Anyone else want to have any concluding statements?
I have a good, potentially good end note, which is I think that we get to declare some success from deep nets, because every lecture to the problem of vision has to change. Yeah. We used to all start our talks with, vision is hard. Computers can play chess, but they can't recognize this chair. And now every intro textbook and every introduction lecture for anyone who ever has to teach vision, we have to completely change the way we teach it. I know, I had to change all my slides. But other than that nuisance, I actually think that does mean, that has to count in a practical way, that they really have made an important step in understanding, because the way we teach it has to fundamentally change now. So, success, in part, at some level of abstraction.
Okay. Thanks to all the panelists.